So we were talking about redox reactions. We talked about how oxidation and reduction must occur simultaneously because it's a transfer of electrons. It's like when you sell something, you can't sell something if there isn't a buyer, right? The money goes from one person to another. So if an atom loses an electron, another atom has to take the electron. So this part with the agents can be confusing, and I apologize. It's not my fault, but I just say I'm sorry for everything because I grew up in the Midwest, and that's what we do. The reactant that reduces another reactant is called the reducing agent, which kind of makes sense. But what's confusing is that the reducing agent is the thing that gets oxidized. The oxidizing agent is the thing that gets reduced. So let's step back from that and think about movie stars and Hollywood. A movie star has an agent, right? And the agent's job is to get jobs for the movie star, find movies for them to star in, right? Does the agent star in the movie? No. The movie star does, right? So the reducing agent arranges for something to be reduced, but it doesn't actually get reduced, okay? The oxidizing agent causes something else to be oxidized, but it is not oxidized. It's the opposite, it's reduced. Does that make any sense? It's confusing, sorry. I didn't make this up. So let's look at these example equations. We're supposed to identify whether they are redox reactions. Not all reactions are. And for the redox reactions, we're supposed to identify the oxidizing agent and the reducing agent. So let's look at the first one. There's several ways you can identify a redox reaction. Here we have the reaction of a metal element and a non-metal element. Is this a redox reaction? What kind of a compound is the product? It's ionic. So do these have charges? Yeah. Do these have charges or reactants? What's the charge on a lithium? On a lithium ion, it's 1+. But this is a lithium atom. It's 0. Do you see a charge there? And then this one is 2 chlorines, but there's no charges, right? So these are elements, no charges. These are ions with charges. So this is lithium and chloride. So we could look at oxidation states, but we have actual charges here. So how does lithium go from being an atom to an ion? It lost electrons. Oxidation is loss of electrons, oil rig. Oxidation is loss, reduction is gain of electrons. So the lithium is losing electrons, it's oxidized. What kind of an agent is it? The opposite. It's the reducing agent. Because the chlorine's going from having no charge to a -1 charge, and it does that by gaining an electron. The chlorine is being reduced, right? So lithium is being oxidized. I'll write this out. Chlorine is being reduced. Anybody have any questions about that part? This is our definition of oxidation and reduction in terms of electrons. Oxidation is loss of electrons, reduction is gain of electrons. We look at this lithium, it started out as a neutral atom, it became a lithium plus ion. In order to do that, it loses 1 electron, so it was oxidized. So this is the first step to figuring out what the agents are. And actually before that, we should answer the question, is it a redox reaction? Yeah, it is. So then we're supposed to identify the agents. So lithium is being oxidized. That means it is reducing the chlorine. Chlorine is being reduced. It is oxidizing the lithium. The agents are opposite of what's happening to the individual. Because the movie star stars in the movie. The movie agent does not. So lithium is being oxidized. It is the reducing agent. The good news is this is not a big deal in the class. So chlorine is being reduced. Thus, it is the oxidizing agent. So you could think of this as, being a movie agent, an oxidizing agent. It's arranging for something else to be oxidized. So let's look at the second one. Is that a redox reaction? Are electrons being transferred? Yeah. Here we have an aluminum atom and an aluminum ion. Here we have a tin ion and a tin atom. It is a redox reaction. We're supposed to identify the agents. Let's first look at who's getting oxidized. Oxidation is loss of electrons. Aluminum's going from a zero charge or zero oxidation state to a +3. It does that by losing electrons, right? Oxidation is loss of electrons. Aluminum is being oxidized. So what kind of an agent is it? Reducing agent. So aluminum is our reducing agent. Tin, going from 2+ to 0, is gaining electrons. Reduction is gain of electrons. It's being reduced. That makes it the oxidizing agent. Any questions yet? Let's look at number 3. Is this a redox reaction? There's a couple ways you can evaluate this. You can look to see, are there ions here, and are the ions becoming atoms or changing their charge? We could look at oxidation states. Here we have an ionic compound and another ionic compound, and they're reacting to form 2 different ionic compounds. We learn to predict products like this. This is actually a precipitation reaction because we have a solid forming here. We took these ions apart from each other and we swapped partners and put them back together. Remember that? It's a double replacement reaction. This is a lead 2+ ion, and over here this is also a lead 2+ ion. This is a nitrate ion. There's a nitrate ion over here. This is lithium plus, lithium plus. Chloride, Cl minus, Cl minus. All the ions are exactly the same. They have just swapped partners. Is this oxidation or reduction? A redox reaction? No. So this one's not redox. Everybody okay with that? Let's look at this one. We have carbon and oxygen forming carbon dioxide. There's no ionic compounds in there. There's no charges. Is that a redox reaction? Yes. Yes, it is. So there's combustion is redox. That's reaction with oxygen. And a metal, non-metal elements reacting, those are going to be redox reactions. The other thing we can do is we can assign oxidation states to this to see, and we're going to have to do that to find out what's the oxidizing and reducing agent. What's the oxidation state for elemental carbon? 0, because all elements have oxidation states of 0. How about this O2? It's also 0. And then we come over here to the carbon dioxide. We have 2 nonmetals. There's no charges involved. So we go straight to that last part, Fe765. There's no fluorine, there's no hydrogen, but there's oxygen. Oxygen gets to choose what it wants. This is how I think of it. And it's going to choose an oxidation state equal to the charge it would have if it was an ion. It's not an ion. There are 2 oxygens. They're going to have the same oxidation state, because why would one be different than the other? So we've got 2 oxygens with -2 oxidation states. What's the oxidation state on the carbon? +4. Because like actual ionic charges, oxidation states on each atom in a molecule have to add up to the overall charge. So now we can look and see, are things changing their oxidation states? Yes. Yes, they are. This is a redox reaction. In terms of oxidation state, I think this is actually even easier to understand. Oxidation means that the oxidation state is going up. It's increasing. Reduction means that the oxidation state is going down. It's being reduced. So if we, yes?
Why is it -2 on oxygen?
Because that's the oxidation state that oxygen prefers. So we can look at the carbon and see that its oxidation state is going from 0 to +4. Is that oxidation or reduction? It's oxidation, right? Its oxidation state is going up. If it's being oxidized, what kind of an agent is it? Yep, reduction, reducing agent. So this is the reducing agent. The oxygen's going from an oxidation state of 0 to -2. That's a reduction in the oxidation state. Negative is going down. So it's being reduced. That means it's the oxidizing agent. Any questions? This is confusing. It is. Especially when you don't use it all the time, which you're not going to use it all the time. And so I think the best thing is to remember the 2 different definitions of oxidation and reduction, and the agents are the opposite. Let's look more at combustion reactions. Combustion reactions are characterized by something reacting with oxygen to form one or more oxygen-containing compounds. Often that includes water. And as you probably know from life experience, combustion reactions also emit heat. If something is burning, it's going to be hot, and you probably shouldn't touch it, right? Here's an example: natural gas reacting with oxygen, forming carbon dioxide and water. So here's our our methane. And we can find the oxidation states of the elements in there. Here's our oxygen. It's going to form carbon dioxide and water. We can look at the oxidation states on those. And we see that the oxygen is being reduced. Oxygen is an oxidizing agent. Oxidation actually got its name from oxygen because it's typically combination with oxygen. Here, the carbon is going from -4 to +4. The carbon is being oxidized by the oxygen. That makes it the reducing agent. And the hydrogen is just staying the same. It's still +1. Nothing happened to the hydrogen. Add a little more to this. So, reacts with oxygen to form carbon dioxide and water. That is true for combustion reactions of anything that contains carbon, hydrogen, and or oxygen. So it may or may not have oxygen. If it's carbons and hydrogens, the products are always CO2 and water. And you just remember that, okay? So let's look at this example. Write a balance equation for the complete combustion of liquid C2H5OH. This is ethanol. So that is our first reactant, so we'll write that down, C2H5OH. We're told it's a liquid, so we'll put that state symbol in there. If this is combustion, what's the other reactant? Oxygen. Oxygen is a diatomic element, and so it's O2, and at regular temperatures, it's going to be in the gas state. We don't take ions apart and swap partners because there aren't any ions here. We just remember what the products are. Carbon dioxide and water. So CO2, and H2O. Now this is not specifically telling us we have to include the state symbols, but it's kind of good practice. What do you think the state of carbon dioxide is going to be? A gas. How about the water? We might think liquid, but when something burns, you see water dripping out of it? No. When you heat something, though, like if you turn on a Bunsen burner or a gas range and you've got something cold above it, what you'll see is condensation occurring. That's the water produced by this reaction condensing on the cold surface. The combustion reaction is hot, and so the water's in the gas state. So there we have our reactants and products, and we need to balance this. So, what color am I doing? I'm doing green. So I saw someone do this in GRASP, and I thought, ooh, I like that. They put the C, H, and the O, the different elements, down the middle, and then they counted up on each side. I like that. So we can just sort of take an inventory here. Over here, there's 2 carbons. And how many hydrogens? 6. And how many oxygens? In the ethanol, there's only 1. And over here, we've got 2 oxygens and none of the other stuff. And over here, we've got 1 carbon, no hydrogens, 2 oxygens, 1 oxygen, 2 hydrogens, no carbons. This inventory technique is often helpful for combustion reactions because there's O's everywhere and C's as well, and so it just gets a little messy. So if I look to balance the carbons, I've got 2 carbons on the left side and only 1 on the right side. So I want to put a 2 in front of CO2, and that's going to change all of the tallies underneath. Then I'm going to look at the hydrogens. I've got 6 hydrogens over here and 2 over there. So if I had 3 water molecules, I'd have 6 hydrogens, then I'd have 3 oxygens. And then we need to balance the oxygens. So I've got 1 oxygen in this ethanol, and I've got 2 over here. That's a total of 3. And over here I have 4 plus 3 is 7. So 4 plus 3, I've got 7 over there. And so I need to do something over here to bring this up to 7. I'd rather not mess around with this one. I don't want to put a coefficient here because that's going to change everything else. I'd rather put a coefficient here. So if I'm trying to make this equal to 7, what does that x need to be? 3. I'll put a 3 up there. And it's always a good idea to double check, but that one is balanced. There's different approaches to solving a balancing problem like that one. Any questions? That was review of balancing equations.